All right, guys, your essential question is how do we approximate the value of a definite integral using a trapezoidal approximation? And your main vocabulary word is trapezoid. All right, guys, if you remember, a definite integral represents the area under a curve for a specific interval, a lower starting number and an upper ending number. If you remember, we approximated definite integrals using rectangles. We used upper rectangles and lower rectangles, or circumscribed rectangles, which were the outside rectangles, so that was the area greater than, and inscribed rectangles, which were underneath the curve, and that was a lower value. And so we used those approximations to kind of determine an interval on which my actual answer would be. However, and this is what's going to lead us into this, is that, remember, you can use integrals to find area as long as you can find the antiderivative of the function. And remember, that's the basis of what we call the fundamental theorem of calculus, is that the fundamental theorem of calculus says that you can find the definite integral by finding the antiderivative and then evaluating the antiderivative with the lower and upper limits. However, sometimes a function is too complicated to find an antiderivative, and that can happen in real life. Even more so, there are times when you won't even have a function. You might just have a table of values. So what we need is a more efficient way to get a better estimate when we cannot find the antiderivative, and therefore you cannot use the fundamental theorem of calculus. Now, let's look at an example. Let's say that we wanted to find the area under the curve 1/8 x squared plus 1 on the interval from 0 to 4. So what it's wanting you to find is the area up under that curve. Now, this function is very easy to find an antiderivative. So we're going to use the fundamental theorem of calculus. So we're going to say the definite integral is from 0 to 4 of my function. I'm going to find the antiderivative of this function. That would be 1 over 24x cubed plus x. And then we're going to evaluate the antiderivative on the limits 4 to 0. And that's going to give me 20 over 3, which is approximately 6.6. So this is the true area under the curve. Now let's look at an approximation. One way we could approximate this is by using left-handed rectangles, or left-handed approximation, where if you notice these are the inscribed rectangles. Notice that the rectangles all have the same width, and it's left-hand because you notice I'm using the first number 0, then 1, then 2, then 3, but I'm not using 4. Now, if I find the areas of each one of these rectangles and then I add up those areas, it gives me 5.75, which is lower, right, than the actual answer. So now let's look at a right-handed rectangle approximation. So notice that it's still width of 1, but this time, instead of using the first left-hand limit 0, I'm just going to use the numbers 1, 2, 3, and 4. And so I can find the lengths of my rectangles, and therefore I can find the areas, I can add them up, and it gives me 7.75, which is too high. Remember, the actual area is 6.6. So how could I somehow average the two and get a more better estimation? Well, one way would be not to use rectangles, but use trapezoids. Remember, a trapezoid resembles this type of shape. And whenever you have a curve like this, it's very nice to draw a trapezoid that hugs very close to that curve. So even it looks like it's actually right on top of that function, it's not. There's still a little bit of space between them. However, this is completely, you can even look at it and tell that that's a better approximation than the rectangles. Now, this leads us into the trapezoidal rule. And this is what it says. It says that you can approximate the definite integral, or the area up under a function from the interval a to b, by using this formula, b minus a over 2n, where n represents how many trapezoids you have, or the number of subintervals you have. B being the ending value and A being the starting value. And you multiply that by f of x0 plus 2 times f of x1 plus 2 times f of x2. That should not be an equal sign. Dot, dot, dot means it's continuous. 2 times f of xn minus 1 plus f of xn. Notice that the first and the last don't have 2, but the rest of them do. Okay? Now, keep in mind that this is important if the intervals and widths are of equal length, and this gives us a better approximation than either the left or the right-handed rectangle. So this is a better approximation. So let's go back and revisit this original function. Now keep in mind that the actual answer is 6.6 repeating. Okay? All right, so what we're going to do is we're going to use the trapezoidal rule, which says that the integral from 0 to 4 of 1/8 x squared plus 1 is approximately b minus a over 2n times f of x naught plus 2 times f of x1 dot 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 plus 2 times f of x to the n minus 1 plus f of x to the n. Okay, well, in this case, b is 4 minus a is 0 over 2 times how many trapezoids do we have? 1, 2, 3, 4 times, we're going to do f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. And remember, the first and the last one don't have 2's, but then everyone else, we're going to put a 2 in front of it to multiply. All right, let's clean this up a little bit. So this is going to be 4 over 8 bracket. All right, f of 0. So we're going to plug 0 into my function. And so that's going to be 0 squared times 1/8 is 0 plus 1. So that's just going to be 1 plus. Now if we plug in 1 into my function, what's that going to give me? That's going to be 1/8 times 1 squared plus 1. But then also don't forget to multiply it by 2. And so that's going to give me 9 over 4. Okay, plus, now we're going to plug in 2 into the function. So that's going to be 2 squared times 1 over 8 plus 1. And then don't forget to multiply that by 2. And so that's going to give us 3. Okay, for the next one, I'm going to plug in 3. So 3 squared 9 times 1/8 plus 1. And don't forget to multiply that by 2. And so that's going to give me 17 over 4. And finally, going to plug in 4 into that. So that's going to be 4 squared is 16 times 1/8 is 2 plus 1 is 3. All right, so now I'm going to add what's inside of my bracket. So 1 plus 9 fourths plus 3 plus 17 fourths plus 3. And that gives me 27 over 2. So I'm going to have 4/8 times 27 over 2. And then I'm just going to go ahead and multiply that. So 4/8 times 27 over 2. That gives me 27 over 4. And I'm just going to go ahead and divide that. So 27 divided by 4 is 6.75. And notice, guys, that our approximation of 6.75 is very close to the actual answer of 6.6.